Okay, now we are going to talk about this idea of log graphs. Now, as we saw a couple of videos ago in the introduction to exponentials or exponents, we saw what an exponential graph looks like. Usually, an exponential graph looks something like this, or, might be some transformation of that, maybe. Point being, exponential graphs generally look something like this. And what we like to do is we like to change these graphs into being something a little more workable, namely a straight line. Now, the motivation for doing this is quite simple. Curved lines are really annoying. Straight lines are really nice to work with. If I have this graph versus this graph, well, yeah, I get a bit more data from this one, but this graph here, I can calculate the gradient, I can calculate the area underneath it, I can do whatever I want. It's a straight line. It's nice and easy to work with. But these things, well, they're quite tricky. So our entire motivation for this is going to be transforming a graph that looks like this, probably not that one, that's a bit rarer, a graph that looks like this into a graph that is a little more easy to work with, aka a straight line. Okay, we're going to start off by looking at a graph of the form y equals ax to the n. So this is an exponential graph where our x variable is having an indice applied to it. So it might be squared, it might be a quadratic, it might be a cubic, and it will probably look something like this, with then a constant a multiplying by it. And remember, we want to turn this into a straight line, so it's a little easier to work with. So if we want to turn it into a straight line, what we are looking for is a y equals mx plus c. That is our straight line graph. An output equals a gradient times by an input plus a y-intercept. So we need to somehow manipulate this into looking like that. Now the way I'm going to do that is I am going to apply some logarithms. Now, it doesn't matter what log I apply, what base the log is in, so I'm just going to use log of base 10 or just log. And I'm going to put both sides into a log. So I have log y equals log ax to the n. Now what I'm going to do is I'm going to apply some of the rules that we learned in the last video. The first rule that I'm going to apply is when I have a log of two things multiplied together. So here I have an a times by an x to the n. Now I'm going to keep my log of y the same because that's not changing. And I'm going to split these up using the multiplication rule. The multiplication rule of logs. And we are going to end up with log of a plus log of x to the n. This is our multiplication rule. If you need a reminder of why or where we got this from, check out the last video. But when we have two things being multiplied, we can separate them into log of one plus the log of the other. Now, the next thing I'm going to do is I'm going to apply the power rule. Now, the power rule of logs applies to any log that has a power inside of it. So my log y is still going to stay the same, equals log of a is going to stay the same, but now my log of x to the n has a power inside it, an indice. So what am I going to do? I'm going to bring that indice down in front. And I will end up with log of a plus n log, I will get rid of that arrow, of x. That power, that n gets brought down in front, and I end up with this. Now, there's no more rules that I can apply here. Everything's been done that can be done. But I can have a look and notice something. I have something to do with a y equaling something to do with an x times by a number plus another number. I have essentially got a y equals mx plus c. This log of y here is my y. This log of x is my x. X and y are always going to have x and y in them. So from this equation down to this one, so we need to be on the lookout for those. And then what am I multiplying my x by? N. So n is essentially my gradient, it is my gradient, and log of a is the number I'm adding on, and it is my c. So what I end up with is an equation of the form y equals mx plus c, meaning if I plot a graph with log y on the y-axis, because log y is in my y position, log x on my x-axis, because log x is in my x position, I will end up with a lovely straight line because I have a y equals mx plus c. No matter what the y equals mx plus c looks like, whether it's got a log in it or a differential or a exponent, no matter what it's got in it, if it looks like y equals mx plus c, it will be straight. We then will have a gradient that we can calculate that is equal to n, again, just by inspection, times by the x value is the n, and I will have a y-intercept of log a. So given this equation, if I were to translate this onto a graph, so a quick example, I'm not going to sketch the details of it, but if I had y equals 3x squared as a graph, so you probably know what that looks like. Well, my a is 3, so I can expect it to hit my y-axis at 3, at log of 3, sorry, log a. So if I type log of 3 into my calculator, it will hit the y-axis there. My n is 2, so it will have a straight line, it'll be a straight line with a gradient of 2, and then it would just be a case of plotting a table, translating y into log of y to plot here, and translating x into log of x to plot here. Now we need to take a look at the other type of equation that will give us a different looking graph, which is where our x value is now in the exponent. So when we plot this with y equals bc to the x, it won't be x is increasing like it was last time. It will be a number is increasing each time with the power of x. So a very subtle distinction. Once again, our goal is to transform this into looking like this, and we're going to do that by applying the same log laws. So first of all, let's throw both sides into a log equation. I'm going to go a little bit quicker through this one. Then we're going to do the same thing we did last time, which is apply the law of multiplication. So this will then be log of y equals b and c to the x splits up, log of b plus log c to the x, and then once again applying the power rule. So we've applied the multiplication rule. X isn't a great, I just put multi, so we know what that means, multiplication rule, and then we want to apply the power rule, and we will end up with log of y doesn't change, there's no power in there. Log of b doesn't change, there's no power in there. But this has a power inside the log. The power gets brought down in front, and I get x log c. And I have something that looks very, very similar to last time, but this time the x is not within the log. So if I map this up here, I have something with a y, so log of y is my y, equals, well, I have x, so my x is just my x is just x, there's no log x this time, it's just x on its own, times by a number. Log of c is just a number times by x is my gradient, so my log of c is my gradient, and then something being added onto that is c. So I have y is log of y, c is log of b, x is just x, and m is log c. Once again, if we turn this into a graph, well, we know from our equation, sorry I didn't write it out again, that log y equals x log what there did I use? C plus log b. So on my y-axis, I'm going to have log of y. Again, I'm going to have to translate all of my y values into log form. But on the x-axis, I've just got x. So x doesn't need to change here. It can just stay as x. And then once again, I'll have a y-intercept of log b. That corresponds to my c. And my gradient m will be equal to log of c. So again, if I had an equation that was y equals 2 times 3 to the x, well, 2 is b, so I know that my y-intercept is going to be log 2. So if you type log 2 into your calculator, give you the y-intercept. 3 is c. Log of c is my gradient. So if I typed log of 3 into my calculator, I would get my gradient. And then finally, x is just x, and that is plotted along the x-axis. So this is how you turn really annoying curved graphs into nice, easy to use straight ones.